Okay, first thing I'm going to talk to regarding station design is piping. And most stations' basic choices are well fabricated and coated steel, well fabricated thin wall stainless steel, grooved end connected coated steel, grooved end connected thin wall stainless steel, and grooved end connected coated ductile iron. And often people simply do it on tradition. Well, that's what we've always done, or client preference. Let's take a look at the various options and put some thought into it. Weld fabricated and coated steel. Um, you're going to end up with a sturdy and clean appearing piping system, but coating the pipe can be tricky, particularly if you've got a lot of elbows and oddball fittings involved. And any future changes can be quite difficult. Remember also that any later welding will adversely affect the coating. So you're pretty much, what you build is a problem to deviate from. Weld fabricated thin wall stainless steel. One of the approaches is, well, gee whiz, we don't have to worry about coating if we use stainless steel. It seems attractive is because it's completely corrosion resistant. And if you use uncoated thin wall stainless, it really isn't much cost difference from coated steel pipe, regular steel. However, uncoated stainless pipe easily dented. You drop something heavy on it, it'll dent, and with time will develop a blotchy gray appearance. And the proper welding of stainless also requires qualified welders that know what they're doing with stainless. Grooved end connected coated steel. Grooved end connections, sturdy, clean appearing system. Easy to coat because the pieces can be divided, the pipe sections and elbows and everything are relatively small, easy to coat, and grooved end system, easy to make changes in the future if you have to. And even though the material costs are a little higher, the labor saving makes it quite competitive in the long run. Grooved end connected thin weld stainless. Same idea that if we go to thin weld now, we don't need qualified welders because we're not welding it. And again, future changes are possible. And you can get galvanized coating from the groove connecting people, which matches up nicely. But again, denting in this future appearance turning to gray is an issue. Number 5, this is something that I myself have never seen done, but something that I would like to see done someday. You don't see it much locally, but apparently in and I'm talking Western Canada, but in Eastern Canada, it's quite common. And it suggests several advantages. Ductile iron pipe is slightly larger in diameter, both inside and out, than steel pipes. You get a little better flow for any given size. It inherently is more corrosion resistant, being iron. Shock tolerant, ductile is at normal temperatures comparable to steel and very close in weight to steel pipe. A typical class SC54 versus Sked 40 steel. So SC54 is ductile, enough thickness that you can groove it, and Sked 40, of course, is steel, assuming cut grooving. You can roll groove, we'll get into that later, you can roll groove steel pipe, not advised. I'm a believer in cut. A wide range of grooved end connections and fittings available specific for ductile iron. Appreciate that most grooved end fittings themselves, including those for steel pipe, are in fact cast of ductile iron, and we'll get into ductile iron, what it is later. Now, if you're going to coat steel or ductile iron pipe, internally and externally, heavy depending upon pipe preparation and coating application. Thus, you need a qualified coating applicator, somebody that knows what they're doing. And this is from specs that I used to use. Contractor shall be responsible and subject to independent inspection, shall employ an AMPP certified coating inspector. Inspection shall be conducted immediately after surface preparation as well as each coating step. After surface preparation, you want to move fairly fast to coating, and only an approved applicator shall be used. And list people that are in the business and have a good reputation. Having coating done by contractor Bob's uncle, unless he's a certified applicator, forget it. And again, this thing about having an inspector and a letter of verification upon completing. Coating is important. Now, pipe. Quick code on metric. Excuse me. While it is common to use a soft conversion factor of 1 inch is 25 millimeters, when expressing the larger nominal inch pipe sizes in metric, there's been a tendency with the smaller sizes to use hard conversion. The preferred soft conversion sizes match DN, which is ISO standard as per the following table. In other words, where hard conversion of an 1/8 inch means 3 millimeter, it's preferred, and manufacturers generally will use the ISO, which is 6 millimeter for 1/8 inch. Quarter instead of 6 is 8 millimeter. 3/8 instead of, it is 10. That's why it's in blue. It stays at 10. 1/2 inch is not 13, it's 15. 3/4 is 20. 1 inch, 25 hard end per ISO. 32 the same, I should have had that in blue. And 38 1.5 becomes 40. And if we progress beyond that, 2 inches 50, that matches. I think the blue was just to break up the chart, by the way. 2.5 is 65, that's the same. 3 inch instead of 75 is 80, and 4 inches the same at 100. Now, steel pipe is basically an alloy of iron and carbon up to 1.7%, formed by heating to a very high temperature and then quenching. Steel is flexible, in other words, ductile, and easily welded. Now, interesting little trick. Up to and including 12-inch steel pipe has a larger fixed external diameter than the nominal pump size would suggest. Look at this chart. Like a 1-inch pipe is not 1-inch OD, it's 1.315 OD. We'll get to the IDs in a minute, and you can see the sizes as we go down. 2 inches actually 2 3/8, 2.375. 8 inches 8 5/8, and 12 inch is 12 3/4 OD. When standard wall thickness pipe is provided, the pipe inside diameter will be very close to the nominal size. In other words, a 12-inch pipe may be 12 3/4 OD, but the ID will be relatively close to 12-inch. The schedule indicates the wall thickness provided for that size of pipe, Sched 40 being the most common, Schedule 40, and agrees with standard wall dimensions up to and including 10-inch, but oddly enough, not 12. At 12-inch, the standard pipe size is Sched 30. Now, for pipe 14 and above, the fixed external diameter is the same as the nominal size. In other words, 14-inch pipe is 14 OD, 16 inches 16 OD, meaning the pipe inside diameter will always be smaller than the nominal size. And I make a note here, the difference between up to and including 12-inch and 14 is a bit of a psychological barrier. A number of manufacturers change design, significantly change prices. There's a mental difference between 12 and 12 and below and 14 and above, pipe and fittings. Now, iron pipe. Iron melts at a lower temperature than steel, and with cast gray iron, carbon 2 to 4% exists as flakes within the iron, resulting in a brittle material. Take a look at the illustration on the right. If you were to look at a microscope at a clean cut of gray iron, you'll find carbon in flakes. As I always say, it's like cord flakes. The milk is the iron, and the flakes themselves is carbon. So if it wants to crack, it will follow a line of carbon, which is why if you break cast iron, and it doesn't take much to, you virtually can't bend it, hardly any at all before it'll break. You notice it looks sparkly. That's because you're looking at all these carbon flakes. Now, by adding primarily magnesium while the iron is molten, the carbon will temporarily form into round nodules. If cooled at that point, ductile or nodular iron is formed. The one time I saw cast iron in quantity being poured was ductile. You've got this molten container, which is mobile, of red cast iron. They pour in with a long ladle magnesium, a bunch of stuff, basically magnesium. There's a little bit of a fireworks show, and then they pour immediately and start to allow the thing to cool once it's been poured. They then do a nice clean, take a sample. They take what looks like a coffee cup, guy with a glove on his hand catches it with the coffee cup into the spigot of iron being poured, It sits there and it starts to turn red from the heat. Then they take it, cool it down, cut it, and look at it with a microscope to see the sizes of the nodules, the circles, whatever. But you can see on the left, now there's not a real easy piece for cracking to appear. And ductile iron is used in the creation of most pipe, can also be used for valves and pumps to provide shock resistance. It also, one of its nice things, it can be poured using conventional gray iron patterns with slightly higher rises. And nowadays, you're seeing in many things, it's becoming a standard product. Automatic control valves, for one, most of them have gone to ductile. If they don't do it as a standard or offer it as an option, it can be expensive to do because it becomes a bit of a special. I've got this picture showing ductile iron pipe. And the one on the left there by the guy that looks like a slinky, unfortunately, I didn't get a picture. You could take the end of that thing and bend it down so that it's virtually pointing 180 degrees. Instead of pointing up, it's pointing down, and you got a circle of the pipe. It is that flexible. I remember a fellow engineer once saying, well, I saw a chunk of pipe fall off a truck once, and when it hit the ground, it fractured, and it was ductile. Why do you know it's ductile? Well, it said ductile on it. I don't care what it says. If it broke like that, it was not ductile pipe. Now, with ductile, the fixed external diameter of iron pipe, ductile iron pipe in almost all cases, is always larger than the nominal size, quite a bit larger. Wall thickness depends on the pressure class, but even at SC54, special class 54, the actuality of the ductile iron pipe is larger than equivalent steel pipes and will thus provide more flow. For example, you can see 4 inches, 4.5 normally. These are 4.8 OD, and at SC54, ID is 4.1. So you can see the numbers as you go along. It is like 12 inch instead of being 12 3/4, actually 13.2 OD, and the ID, instead of being around 12 inches, 12.34. So you do get more flow out of it. These are into the larger sizes. At 20 and 24 inch, instead of SC54, you need to go to SC55. Now, connecting. Threaded joints. Pipe is usually threaded to NPT, National Pipe Taper Standards, the taper being 3/4 of an inch per foot. Because of the thread form, NPT joints are not intended to be drip tight unless a joint sealant is used. If you use Teflon tape, which is quite common, 2 to 3 wraps. I've seen, and there was a problem at one time, people will put several wraps on, think, oh, we get better sealing. What happens is the Teflon, because it's in so loose, will actually move a little bit under pressure, and a few months later, you got a leaky joint. So 2 to 3 wraps is preferred. A significant problem with any threaded joint is that the makeup depth of the joint, even with thread gauges, is rarely perfect. So the length of a collection of threaded fittings can vary. Threaded pipe joints should never be considered for pipe over 2 inch, except for well pumps. Well pumps have the reason because you're trying to stay within a confining space of the well, so threading is quite common. And to be frankly honest, if they leak a little bit, it just goes back into the well. Flange joints. In waterwork, common flange sizes are class 125/150 and 250/300. Now, at a specific size, say 6 inch or whatever, excuse me, all 125, 150 flanges will bolt together. But the cold water rating, cold being 65 degrees C for cast iron, 40 degrees C for ductile or steel, the pressure ratings will vary depending on the flange material. Here's how it works. You've got a class 125, which is iron, cast iron. There's actually 3 different standards, one for cast iron, one for ductile, one for steel. ANSI B16-1 basically allows 200 psi if you're using those flanges. Ductile goes to ANSI B16-42. You're good to 250 pound with class 150. And as I say, 125, 150 will bolt to each other. And in steel, you're up to 2, which is ANSI B16-5, you're up to 285 psi. Note at class 125 cast iron, the rating goes up or goes down at 14 or over to 150 psi. Similarly, all class 250 or 300 flanges will bolt together. But again, the cold water rating will vary depending on the flange material. In class 250 gray iron, 16.1, 500 psi, 14 and above 300 psi, class 300 ductile 640 psi, class 300 steel 740 psi. Note that the cold water rating of a flange is always much higher than the class number, which relates to the flange saturated steam pressure rating. Because it's right in front of us, let's take a look at, say, the class 300 ductile. You say, well, that's good for 300 psi because it's class 300. No, it's good for 300 psi dealing with saturated steam, which we never do. When you're dealing with cold water, and a cold water, again, you've got the values up above, at cold water rating, 640 psi, well more than double. Okay? Now, class 125 flanges, which means cast iron, gray cast iron, are always flat-faced. That's because of concern of cracking if you don't go with a full flat face flange and a full gasket. All other flange classes, including the 250 gray iron, you can use a raised face, which, as you can see, gives you more pressure over a specific area, and a insert what they call a ring gasket, because you're not worried about cracking the thing by over tightening the bolts. Welded joints. Welding, of course, is possible with steel pipe. That's a big thing with it. Appreciate conventional welding as a filler, not a glue, and you should have a V-shaped joint for proper application. You can actually get rings with little spacers in that you would put between two ends of pipe, and basically that's used as a bit of a filler when you weld the thing and make sure you've got the proper separation. So it's actually, they have to be V-shaped, the joints. There's a bit of a trick to do it properly. And if you notice, the fittings will allow for that, an angle joint. There's different flanges available for welding to the end of a pipe, including lap joint and socket, but the most common waterwork styles are either weld neck or slip-on. Weld neck, shown on the left in the diagram, is inherently stronger and more elegant. It looks nice. But slip-on flanges, usually adequate, more compact, and do permit some deliberate misalignment. It's quite common with slip-on. You got the pipe there; it's right up or very close to the flange on the pump, and you take a slip-on, put it up against the flange on the pump, and then loose bolt it, and then weld it. And if there's a bit of an angle, it's there forever. Okay, fine and dandy. Now, there are a number of people that do groove joints. I'm going to say Victaulic because, with one exception, they're the only ones I would accept, the other one being from Grinnell. Victaulic comes from Victory Hydraulic, and the concept goes back to the laying of water lines in the trenches of World War I. I think it was 1919 that Vic was created, somewhere close to just shortly after World War I. And basically what it does, it uses a multi-piece clamp to retain grooves in each pipe end and thus prevent separation. The gasket used does not rely on clamping forces to make a seal. It has two inner lips. You can see on the upper left sketch there, unique C-shaped gasket. So it has two lips that fit on the ends of the pipe. So you put that on, with the pipe in. Then you've got the coupling itself, which retains the grooves. Because it's a lip seal, internal pressure causes the thing to seal even better. And you end up, if the surfaces are half decent on the end of the pipe, then you will end up with an absolutely grip tight seal. We got into it at one time because we're doing package stations and booster units, whatever, and you bolt it together with flanges. And by the time it got to site, the first thing you did is spend an hour to tighten up all the bolts because they loosened. With grooved end, no. It'll test drip tight, and after being shipped, it will be drip tight. And the clamp bolts don't have to be super tight. Say even finger tight. Well, you want a little tighter so they don't just magically fall off, but they don't, that's not what's making the seal. Now, the original flexible coupling allows the two pipe ends to move a little bit and move in and out a bit. That in and out is from touching to about 1/4 of an inch using cut grooves. Because of that, you're also allowed some angularity. Now, rigid couplings, for a long time, this was one of the, it was a plus and a minus at the same time. If you've got a lot of couplings, you ended up with too much flexibility because that 1/4 inch can add up. So developed were rigid couplings. And basically, if you look at the where the bolt is on the left there, you can see that the pad where the two coupling is at an angle. So what actually happens is you tighten the thing, it twists each coupling a little bit up against the groove, so to block it at about half the range. In other words, where it's typically 1/4 inch, it'll be frozen at about 1/8 of an inch. The flanges are neat. Flange adapters fit onto the end of your groove pipe. And again, the gasket you can see is sort of almost like a funny C-shaped thing on the sketch on the right. And it seals against, at the bottom, against the outer surface of the pipe between the groove and the end of the pipe, and seals up against the flange that's coming towards it that you want it to go to. These flanges permit positioning of the flange holes as desired. You can rotate it as you want. And again, done properly, a drip-tight seal. One should be aware that a smooth, hard companion surface is required. In other words, where it contacts the fitting or valve or whatever it's going up against, that needs to be in reasonably good shape. Another thing with these flange adapters, though they do have little teeth, give them enough torsional force and they can actually twist. We're showing grooved in flange adapters again, and they have the advantages. They say they can be rotated, they have a dynamic lip seal, drip tight, and they're easy to install, very easy. And again, as we suggest, they can't tolerate significant rotational force, like if you've got a T with a valve in one end. We had this happen once. That's enough rotational force that it actually rotated the thing down. And it requires that what you're bolting up against be suitable. Rubber-faced flanges, valves, etc. require use of a flange washer, which is basically nothing but a chunk of steel, like a big washer, so that the valve, let's say you've got a valve that either has a rough surface or something, but rubber-faced, is going against the washer, and on the other side, the Victaulic flange adapter is going against that nice smooth washer. Now, I like grooved-in systems. Why? Flexibility can be provided where desired and changed later. In other words, you can use the rigid couplings all over the place, except where you want flexibility, you can go to the conventional coupling, which allows this 1/4 inch of movement. The pressure ratings are high, minimum 300 psi, and you can get well beyond that. Coating pipe spools fitting, easy pre-coat because the headers or whatever can all be disassembled into a collection of easy to coat pieces. Assembly skills are minimal. You got to remember to lubricate the gasket. The rubber part has to be lubricated so it can slip, and that's about it. So field assembly is quick and easy. The weight of components is less. With good contact surfaces, the assembled piping system will be drip tight, and disassembly and reconfiguration is facilitated. It's easy to do. Now, there are grooved-in systems available for both steel pipe and iron pipe, but their coupling and fittings are not interchangeable. Because of the different OD of steel and iron pipe, you can't use one on the other. And here's a situation where actually, if you look at it, on the left-hand side, there was a chunk of steel pipe, but the valve on the other end had been grooved for iron pipe. So the coupling in between didn't know which one. It's going to lock onto the iron valve because it's larger, but therefore you're going to have a leak on the left where the pipe is. There are transition couplings available that allow you to go from steel pipe to iron pipe grooved ends. And there's a little blurb on it there. Fittings Pretty large variety. Best to design around the commonly available fittings wherever possible, such as standard 90 elbows or long range 90 elbows. Um, it's much like in welded. Believe it or not, in welded, the standard elbow is long radius. With Victaulic, you can get the figure 100, which is a long radius and is not that expensive. 45-degree elbow, standard tees, reducing tees, concentric reducers, and caps. All those are pretty much standard fittings from Victaulic. Now, talking about piping systems, a general guideline for sizing inlet and discharge piping to a pump is you would like a minimum inlet velocity of 2 feet per second to keep debris suspended if you're dealing with wastewater, and a maximum of about 8.2 feet per second, again on inlet piping. With clear water, the discharge velocity limit can safely be extended out to about 13.1 feet per second. Okay, what I'm saying there is the inlet velocity 2 and the maximum discharge of about 8.2. But you can go higher in clear water applications safely to about 13 feet per second. Appreciate rather than using long sweep elbows and laterals to reduce friction head, they may look neat. The same or better effect can usually be provided simply by increasing piping by one size. Size by velocity, not stylistic. Now, plenum chamber. A plenum chamber is a housing containing a gas, typically air or fluid, functioning to equalize pressure and flow for more even downstream distribution because of irregular supply or demand. If you've got a large enough header, flow patterns will be dissipated and it can serve as a raw source for the supply to pump inlets. In other words, it becomes almost like a wet well. What I'm showing here, by the way, just because this is a picture of the engine of my boat, tunnel ram, and you'll notice that there is large chambers underneath the carburetor, which then go down to just above the valve covers. You can see the individual pipes that go down. It's cast as a single second assembly. But what that volume does is allow the carburetors to have a much smoother flow. Instead of seeing the pulses of the cylinders drawing air, it sees it as more of just a general vacuum because that plenum chamber has got rid of all the pulses. So the idea of using plenum chambers can be very useful in piping systems. Header branches, yes, as I say, you can, if you've got a plenum chamber, come right off the header if it's big enough. This allows individual pump inlet to be designed for desired flow characteristic from the header only. While lateral fittings are sometimes utilized on the left to reduce potential head loss, and they look streamlined, in fact, selecting larger T sizes for reduced flow rate will often result in lower head loss and less expensive. Okay. Thrust and support. Unlike bell and spigot connected pipelines, which require thrust restraining, pump station welded flanged or rigid grooved end connections are inherently pressure containing. Standard grooved end couplings provide, as I mentioned before, about 1/4 inch of movement, which also permits some angular misalignment. Both standard and rigid couplings are interchangeable. The station designer can kind of design using grooved end where he wants flexibility and where he doesn't. It's useful to have them at where you want to remove equipment. That 1/4 inch gap will help you pull, say, a pump or valve out. Also good at elbows. That provides a surprising amount of flexibility if you use flex couplings on an elbow. And in terms of support, custom-made pipe supports can be called for, but manufactured adjustable pipe supports do allow a degree of quality control. There are companies that do make factory pipe supports. The location of support should also consider the effects on equipment removal. And that's about it for piping. I do hope you've enjoyed and have a good day.